Okay, it's a pleasure to be here. So this morning I will. So yesterday I had an introduction from Marco about surging, let's say, heavy dark matter particles with mainly dual phase DPC detectors, liquefied noble gas. Now we try to move slowly to more lighter candidates. And then later on, Belina will go on with even lighter candidates and technology to push the threshold even further. So I would I will give a short introduction, since yesterday there was already a lot of things said about experimental detection. I would just pinpoint few issues which I'm not sure were covered yesterday, and then we move to the experimental activity. So this you probably have seen many times, the way we can look for dark matter particles. Of course, here the question is if this interaction does exist, if the two sectors doesn't speak to each other, then my job is kind of over in some way. But let's say that there is a way the standard model, the standard sector interacts with the dark sector. So the way we have to get in contact with particles from the dark sector is through production, so colliding standard model particles and hoping to produce particles from the dark sector through scattering from dark matter particle from the galaxy halo onto nuclear particles. And the other way is the opposite of production, that is annihilation of particle-antiparticle in the dark sector. These methods are not actually the same, because to probe the halo composition, so to probe what is the content of matter that we are missing in the universe, we need to go through one of these two, while in this way we can access probably even particles that are not necessarily component of the halo, and we can in some way study. So these technologies are complementary, but if we want to gather information of what is composing the dark matter halo around the galaxy, and so gather info on what's really generating the gravitational effect we observe in the universe at many different lengths, we need to go through some kind of direct and indirect observation. But I will say that direct detection is the crucial way to access informations on the composition of the halo. Okay, this you probably heard a number of times already in these days. We have many information on what this particle should be. These are actually small constraints. So the fact that we extract information on the fact that it should be non-baryonic dark matter that has to be cold, that we do see gravitational effect, and it's still with us. So it's either stable or extremely long-lived. All these constraints are actually constraining very little the dark matter candidates. So you will hear, or you heard, and we will hear again in these days, there is a variety of theories, models, guess, or what this particles should be. And this is just few of the families of theories and models that are out there. Of course, not all the proposed solutions are at the same level. Some are theory, which are based on robust hints on observation and constraint from the standard model, for example. Many are just models, empirical, semi-empirical models. Some are just guess, just hypotheses that cannot be ruled out at present by experiment, but they're not strongly theoretical motivated, but they're just still possible. So, of course, it's very good to have these studies, because to push experimental research in different direction, it's very important that people try to understand which are the possible candidates that can populate the all around us. So, and I hear this is a quote of my master thesis mentor: never trust theories, just measure. Of course, this is a little bit experimentally biased, but yeah, the story. So Ettore Fiorini was one of the big person in astroparticle physics in Italy, and he passed away a couple of years ago. And the story he used to tell to every student at the beginning of the thesis was, listen. So he was one of the person who made the Gargamel experiment. So the first observation of neutral weak currents. And after the Gargamel experiment, the electroweak model was awarded with the Nobel Prize. So Glashow, Salam, and Weiberg in some way get their Nobel Prize due to Fiorini and collaborators. So he was in very good relation with Salam in particular. And after the Nobel Prize, Salam went to discuss with Fiorini at the Department of Physics in the Milano University and tell him, look, proton is going to decay. Trust me, I did the electroweak model. Everyone should trust me. So at that time, in the 80s, there was an international collaboration that built the first proton decay experiment in the Mont Blanc laboratory. So this was before the operation, the fully operation of the Gran Sasso lab. So there was no large laboratory in Europe and almost in the world, and people was using these tiny boxes and side tunnels of the highways. So they did this proton decay experiment looking for proton decay at 10 to the 26, maybe 10 to the 25 years. And you will know nowadays that for sure proton is on decaying up to 10 to the 33 or 34 years. So after that, Fiorini was always gathering students and take them, have all sit and listen to me, never trust theories, because we did the proton decay experiment and proton didn't decay where we expected. This is just kind of a joke, of course, but it's clear, and you will hear in these days, and one of the reasons I really like the approach of this school is that we put together the way we understand things and the way we have to measure things to make to confirm the understanding. So in some way, my personal view is that the current attitude, the fact that now we look in an absolutely open-minded way of all the possible models, is much more scientific than it was the age of the WIMP miracle. WIMPs and supersymmetry are there. Maybe not today, but tomorrow we will see supersymmetric particle, and the day after tomorrow, for sure, you will see dark matter neutralino. This was 30 years ago, and there was really a non-super scientific attitude in picking experiment and encouraging some direction of measurements. So after quite some years, nowadays, we know less than we knew probably, or we thought we knew, but we are more scientific on the approach. So this is, I think, it's a good age to look for dark matter. Which is the downside? Well, the downside, this I guess you heard already. Possible candidates for dark matter at present, but I'm sure that you will develop either more fancier models and ideas. They span on some 50 order of magnitudes in mass. And this is quite a large range. I think it's one of the largest range of planetary interspace that you can look for. And of course, to do experimental research, in such a huge range, you have to use completely different experimental approaches. So what we do nowadays, or what we did mostly in recent years, it was to observe particles in the original WIMP miracle region, that is around, let's say, 10 to 100 GeVs. So it's a very narrow region down here around the GeV, but there is still a lot of different ranges. And of course, if you move, so I will get back to this, but if you move to very high particles, what is killing your experimental capability is the density. We know that the local density is about 0.3 GeV for cubic centimeter. So if your particle is 1,000,000 GeV, this means that it will be very challenging to have one particle crossing your detector. And if the cross section is that low, you need, I don't know, cubic kilometers of detector to be able to detect few particles. On the other side, if you move to completely different concept like axions or axion-like particles of what they call fuzzy dark matter and so on, you need completely different experimental approach. So you don't have a detector that is good to span all this region. So this is also important because you have to be aware when you decide to measure something, which region you are measuring, why you are just picking that region, and so on. So one question is, why do we look in the WIMP region? It's just, we're almost blind and we just throw our arrow somewhere, hoping they will get something without really seeing. It's not really this way. We started from the mass region of all the particles we know. All the particles we know, we know now thousands of particles, and all of this span around, let's say, if you start from neutrinos, you go from the electron volt scale to the TeV scale and slightly above. There is nothing that we know that goes to micro electron volt. There is nothing that we know that goes to the Planck mass or whatever. So, and of course, we started from the region of our target. This is a matter of fact. We had the capability of measuring that region, so we started to explore the parameter space from the technology we had. And we started from the possible theoretical scenario, which was the neutralino supersymmetry model. And so I think the approach was not bad, but of course we must know that this is not the only option. So this you heard a lot in these days, so I will not go into this. One thing I want to stress is when you compare direct detection experiment, so sensitivity of different experiment, if you do something with liquid xenon, as you heard yesterday, or sodium iodine crystal, or superfluid helium you will heard about, you need a common scenario to compare the experiment. So you compare experiment under some assumptions. You pick your favorite halo model, you pick your favorite interaction, and then you treat the data according to this assumption, and you can compare the experiments. Otherwise, it's really difficult to compare the result of different experiments. Okay, again, this is something you heard, that the standard assumption is the density, the local density as 0.3 GeV per square centimeters, which is, of course, very little in daily life units. And of course, the detector size can change quite a bit depending on which kind of particle you want to observe, which sensitivity, which threshold, and so on. So just to give you an idea, this is few options for dark matter particles, which are even in the low mass range side, what people sometimes call light dark matter. So if you have a volume of a liter, your milk volume, you end up having something like 300 particles in your volume if the mass is 1 GeV. It just goes down to 60 for 5 GeV, 30 for 10 GeV, and so on. And so if you can scale this. So, of course, if you want to measure 100 GeV dark matter particle, 1 liter of volume is really not enough. And that's why you heard again yesterday that xenon or argon people is moving to multi-tons experiment. So several cubic meters of, so thousands of liters of active mass. Okay, what controls the rate are 2 factors: the strength of the interaction between baryonic and dark matter, which to our constraint, to our understanding, is in the sub-weak scale, or should be there, but there are different also options. And of course, the efficiency, the capability of detecting of the detector medium for the specific energy you're looking at. The lighter the dark matter particle, the lower the threshold you will have to achieve. So if your threshold is too high, there's no chance to measuring very low dark matter masses. I will go back to this also. Just one comment, this I mentioned about comparison, but many times, at least in the experimental dark matter community, we hear people discussing of model-independent observation. I think experimental data are model-independent in the sense that you place a detector, you measure something, but the interpretation of data is always done under some assumption. The HALO model itself, we have reasonably constrained HALO model, but still there are a large number of tiny or even not tiny exotic variation on the distribution of velocity and particles in the HALO. And this is an assumption. So whichever model you pick is not anymore model independent. And whichever HALO you pick is not anymore model independent. So just to give you an example, this is a place full of theorists, so I will not go into the details, but just to see something that catch my attention in recent years. The modulation signal we expect is under the assumption of HALO composition and the particle, the dark matter to ordinary particle interaction. But you can pick interactions that this is some paper from Katie Fries and collaborators. You can pick interactions in which the phase of the oscillation is shifted, or even the amplitude is shifted. So you get to variation that completely change even your modulation. So even modulation is not a model-independent observation. It depends on the interaction you pick and the HALO you have. So just to say that when you look into data, you have to pick data with grain of salt. That's very simple. Okay, this you heard a lot, so I will not go into the details. We are basically mostly looking on scattering over nuclei. Also, scattering over electrons has a good channel to detect lighter dark matter particle. But most that you will hear about direct dark matter experiment is scattering of dark matter particles over electrons. With the velocity in the galaxy, and the easiest model is elastic scattering, and also here the interaction can become more and more complex. Then let's say the first level increase of difficulty is spin dependent scattering, and then you can make it as complex as you want. And this also, you see how this is extracted, just to remind about the rate you expect. This is under elastic scattering condition, standard HALO, everything. You have information that come from the HALO, so the local density and the velocity distribution. You have a component that is the nuclear form factor, so the way your detector is done, and you have the ingredient from your WIMP candidate, so the mass and the cross-section. This experimental challenges, so this is how the expected spectrum change for different dark matter masses, 10 GeV, 100 GeV, 1000 GeV, simulated with a calcium tungstate crystal target and ideal detector, so nothing strange. And you have, of course, very, very rare rate. So you're looking for events at present limit in the order of counts per ton day and even lower. You have a spectrum which is with no special features, no special peaks that can help you in disentangle, and this is at very low energy, typically at the threshold of the detector. This is another problem because some kind of fluctuation near the threshold in an experimental, in a real detector is something very common. And of course, near the threshold, the behavior of the detector is usually tricky. That's why you cannot push the threshold even lower. So having a spectrum that doesn't have any nice feature, it's making your hunt more difficult. And of course, the release and the energy is very small. We go from the keV range to much smaller energies, depending again on the mass of the particle. Here you can also see what I was mentioning before, that once you set the threshold of your detector in energy, this makes some dark matter mass inaccessible. So if the threshold of your detector is around 10 keV, sorry, this makes almost impossible to access 10 GeV dark matter particles, and even lower. So the lower the mass, the steeper the spectrum, the most difficult is to access in terms of energy release. This is one of the exclusion plots, is probably not the most up to date in terms of result, but basically, this is just to say that the sensitivity to dark matter nuclear interaction scales with exposure depending on your background level. So in the, let's say, high dark matter particle mass, 10 GeV and above, mostly you are dominated by exposure, so how big is your detector, how many nuclei you have inside your detector, and by the level of background inside your detector. But if you move to lower energy, as we just said, the threshold steps in as a relevant ingredient, also because your expected spectrum is quasi-exponential. So the lower you go in threshold, also in terms of, for a given dark matter particle mass, the lower you go in threshold, you increase exponentially the number of interaction you expect. So threshold has a role in this game. Of course, if you move to very high particles, then your limitation is, as we were saying, the density. So there is not much. You have to increase a lot the detector mass to hope to get particles. Okay, what we had this titles about heavy or light dark matter. So what is light dark matter? I will say there is not a really established definition of light dark matter. So I think that at present people call light dark matter compared to the standard WIMP scenario, which expect particles to be within 10 and 100 GeV mostly. So whatever is below this number to, I don't know, few tens of MeV goes under the name of light dark matter. And there is nowadays some theories or models that support this this kind of dark matter masses. So it's not just randomly picked. Asymmetric dark matter, for example, again, it's not, I don't want to touch too much theory because I'm mostly an experimentalist, but the fact that even in the dark sector, that can be the same asymmetry that we have in the standard sector between matter and antimatter, because there is some kind of common origin. It's some reasonable way of thinking, I think, and this opens, for example, the way of the presence of light dark matter particles, and there are a number of other models in which light dark matter particles are not disfavored. So in the, let's say, heavy dark matter region, the dominant at present technology, so the technology that brought the most sensitive results in terms of measuring are dual phase DPCs based on liquefied noble gases, and you heard from Marco many details about this. On the other side, in light dark matter particles, there are a number of technologies. Let's say the most, the historical one is cryogenic detector. So one of the first technology to be developed was in recent years tuned to move to light dark matter particle. But in recent times, people came with new and old ideas to try to catch these particles. And basically, this part was covered yesterday and by Marco. I will try to cover a little bit in between with some preference with cryogenic fuel, cryogenic detectors. And then you will hear later on from Bellina something about this even new idea, well, new, old ideas, but then now are becoming new experiment like superfluid helium, some cryogenic detector, and maybe also gaseous helium TPCs. So time projection chambers. And yeah, this is usually dual phase. So you have a liquid part and a gaseous part. These detectors down here are spherical TPCs with high density, high pressure gas inside, helium gas. So low target mass, but this again will be covered by Bellina. Experimental signature, again, you heard a lot about this. Spectral shape, it's not really catching us too much because it's a very simple rising semi-exponential spectrum. The annual modulation rate is in principle a very good signature, but of course depends on the way the halo is made and the interaction is made. And one thing that can also be interesting to exploit once we will have a signal is the direction of the interacting particles. This can help us to pick, to reduce the background, because in principle we are moving toward, let's say, Genius constellation. So we move in that direction, so particles come from that way. This is the what we call the nuclear form factor. So this is depending a little bit on the individual nucleus on which you have scattering. This, I guess Marco covered a little bit of this yesterday, but this is also, this kind of features depends on how narrow the tips are and so on. So it's not obvious that you can very easily disentangle some form factor to another, but when you do the fit of the spectrum, you try to take in account also this. But there is not a signature that is so evident that you will pick that nucleus, because it gives you some feature that helps you a lot to disentangle to other kind of interaction. Backgrounds also, you heard, I think yesterday, quite a bit of things, so I will mostly skip this part. In practice, dark matter direct detection experiments are operated until they're background limited. So you have then to improve, so reduce the background level, because keep measuring with that detector doesn't increase your sensitivity. So reducing background is basically a full-time work that keeps going every time. You don't just also for liquefied noble gas, you just don't build a bigger pot, but you need also to accordingly decrease the background. Otherwise, you get to the same sensitivity. And of course, this is why we keep searching for new ideas to push the sensitivity ahead. So this is what happens. You have you keep increasing the sensitivity with exposure until you get to some level of background. At that point, your exposure doesn't help increasing the sensitivity. So, of course, for making a discovery, so you observe some kind of signal, is mandatory to understand the residual background, resolution, position, reconstruction, background modeling. So depending on the kind of detector you have, this, if you just want to push the sensitivity, you have a low background, but since the goal is not pushing sensitivity, but detecting dark matter, this part is not negligible. Whichever signal you observe, then you have to constrain it, and you will see later on an example of a signal that needs to be proven. This you heard. The first background you have to reject is cosmic rays. So you typically go in underground laboratories, and there is a number of underground laboratories around the world with different depth. Let's say for detectors with online response, so you get the time information on the event interaction. You can help the effect of the mounting or the ground shielding of cosmic rays with some tagging of the incoming or rejection of the incoming radiation. So what people call sometimes artificial depth. So you increase the shielding around the detector to reject more background than what your mountain or your mine is capable to reject. So it's true that being in a deeper lab helps, but there are ways to help, let's say, your fancy Italian lab to push sensitivity even deeper than just yeah, so the numbers you have in terms of well, I don't have the number here, but let's say at here, roughly at sea level, let's say you have some 1 muon per square centimeter per second. Roughly, this is the typical rate you have, and if you go, of course, the higher you go, the more this increase. But roughly at sea level, you have this number. At the level of Gran Sasso lab, you have a factor of about 1 million of reduction of this number. So you get down to 1 muon per square meter per hour. So, of course, what is I don't know if I mentioned this here, but what is relevant for dark matter experiment is not the muon itself, which you can easily tag with muon vetoing of some kind, but is typically radiation that can mimic dark matter interaction. So neutral particles, neutrons basically. So muons can induce neutrons through spallation, for example, in the rock, even in the shielding of your experiment. So you build a nice shielding to protect your experiment, and the muon induce in your shielding a neutron that mimic the dark matter signal. So that's one of the issue why you want to tag a muon, even if it's not your typical background, because if you can get coincidence rejection of the muon crossing your shielding, for example, then you can tag the event generated in time coincidence, the neutron generated by spallation of the muon in the lead shield, for example, as a neutron and not... then there are other ways. Just one, let's say, curiosity about backgrounds. Nowadays, we start speaking about neutrinos background, which in some ways seems amazing. And for this kind of background, just in summary, there is nothing to do. There's no way to shield the neutrino background. Even if you are in the, you have the sun as a shielding, it's no way. So there is no shielding technology that can reject neutrinos. So basically, you have to live with neutrino background. And this is what you expect from neutrinos. This is things that maybe you know. The most intense source of neutrino is the pp cycle. So proton-proton fusion in the sun core, basically. And the energy is low, but the flux is extremely high. You have really a lot of events per ton year at 1 electron volt threshold. On the other side, atmospheric and diffuse supernova neutrinos has much higher energy, but the flux is much, is much lower. So you are of the order of few events per 100 ton year. So you have a balance going up this curve of what you can see, but you have to live with this. What I find, this is the so-called neutrino floor expectation. So where these curves are, where you have to expect to see the first one neutrino event in your detector. And basically, in less than 100 years, neutrino pass from being an hypothetical but not detectable particle. You remember probably the comments of Pauli about making the hypothesis of a particle to explain what they saw at that time to the radioactive community that cannot be detected. Then it was actually detected just 25 years later by Cohen and Ryan. Then it became a hard-to-detect messenger from the sun. In the, let's say, 70s, Ray Davis Jr. made the first detection of solar neutrino with the chlorine experiment in the Homestake mine in South Dakota in the US. And then it became a deeply studied particle for oscillation, and the SNO experiment at McDonald, Ray Davis, many of these guys got just a fancy Nobel Prize medal for their studies. But at McDonald and the collaborators get to disentangle the oscillation, neutrino oscillation puzzle with the SNO experiment in 2001. So let's say recent years. And just last year, the Xenon collaboration announced the observation of the first neutrino background event in the Xenon Anton detector. So, okay, 100 years seems a lot of time, but we pass from a particle that we will never be able to detect to a particle that is our background nowadays to doing experiments. So that's to give you a taste of how increasingly our capability of detecting and understanding the world around it's grown. So this is in some way. Yes. Let's say you don't know. It's impossible to disentangle. That's correct. So they had the first event, which it's compatible with the neutrino scattering and is consistent with the expected neutrino rate in the detector. That's basically what they claim. It's the first one. They now have some fewish of them, which is compatible with the expectation on the neutrinos. Then, of course, if you have dark matter exactly at the same level and rate of the expected neutrino, let's say 50% is neutrino, 50% is dark matter, but It's correct. In fact, the way you live with this background is just you have to look at the features of this background. And this, for example, at this point, directionality or annual modulation came out as an interesting feature. I will say annual modulation is the first way you cross-check your background. It's clear that if you're at the level of one event, is not, your mass is not sufficient to test this. But if you go to 100 events, so you probably heard in these days that in standard assumption, the oscillation rate you expect is some 7-8% of the signal, because of the components of the different velocities. So on one event, 7% is not a good way of testing the variation of the rate, the seasonal variation. But of course, if you get to 100 of events or more, then at that point it becomes more detectable. So, of course, in next generation experiment, neutrino can be both a background and a signal, because there is still some solar star physics that we are interested in. Metallicity, for example, other open question in the understanding of the life of stars, and of course can be supernova neutrino detectors monitoring nowadays multi-messenger, what people call multi-messenger astronomy. So getting signal, for example, from a supernova explosion in many different type of radiation helps a lot to constrain the process of the supernova explosion. So people, it's looking to see some galaxy explosion with a strong signal in neutrinos, visible gravitational waves, and so on. So it may be not the main purpose of the next generation of detector, but will be a nice feature that this detector, especially like this huge cryogenic liquid detectors, can exploit. Another thing about, so you heard yesterday about all radioactivity. I won't go into that. That is the main source of background, typically in this kind of detectors. Dark matter, light dark matter, so low mass dark matter, open to new challenges, because we move to this region here from, let's say, hundreds of electron volt to tens of electron volt. So alpha particles are in the MeV range. Muons, this depends, of course, on the part of the detector they cross by, but usually the energy is few MeV for centimeter gram. So it's easy to release higher energies, or you can cross-check with other muon vectors, nearby detectors, and so on. Nuclear recoil, so the recoil of the nucleus that is emitting alpha, for example. If you have a detector that is in vacuum, you have your nuclear recoil goes to inside the detector, and your alpha particle escape and goes away if the decay is on the surface, and if the detector is in vacuum. This is typical of cryogenic detectors. So you have to operate, we will get back to this, but you have to operate detectors at tens of millikelvin. So to reach this temperature, they have to be operated in vacuum. So at that point, the good thing is that you are in vacuum, but the bad thing is that you are in vacuum. So you don't have active background rejection around the detector. So nuclear recoils can become a issue if your detector, has contamination on the surface. And then you lower, you have the contribution of beta gamma events. You have atomic physics stepping in, so X-rays. But if you still go down, we have really no idea what's becoming the dominant background. In this tens of EV, you have what? Lattice dislocation, molecular phenomena. Basically, it's really an unexplored region of. So you find new ideas to to explore new parameter space, but really you open a door to a dark room where you have to discover everything. So you have to deal with understanding what's going on down there. Yeah, this is again nuclear decays with beta emission, and this, yes. But you, they're important as a background. Basically, the idea here is just a beta decay goes down to 0 because of the splitting of the energy between the electron and the neutrino. While in the X-rays, typically your value is fixed by the atomic shells. So yes, but of course, given to the physics, betas and gammas are converting into one another continuously. But basically, and of course, this, when it goes very low, gammas became X-ray, of course. But X-ray emission from atomic physics has fixed values that are related to the the atomic shell population, of course. Okay, this I think you heard yesterday. Material selection is crucial issue. This is related mainly to the radioactivity content. So you need both screening capability and cleaning material technologies. This is a very important issue. This is true not only for dark matter detectors, but in a variety of experiments in astroparticle physics is the fact that dark matter detectors usually are typically more sensitive. So your final detector is more sensitive than any screening technique available on the market, let's say, where the market is typically astroparticle physics labs, not other than that. So usually if you buy copper, just example, copper, vendors certify coppers to contamination at the level of becquerel. You have copper samples guaranteed at 1 or 0.1 becquerel. You are looking at something with contamination in micro or nano becquerels. So what you get on the real market is nothing that you can be useful for you. So in underground laboratories all around the world, not only in Gran Sasso, you have screening facilities that can push the sensitivity quite below any commercial vendor can guarantee. But on the other side, still what you need for your final detector very often is lower than any screening technology. So you do all your best to select materials, but typically you want a way to active disentangle the presence of possible contaminant. Same concept. If you cannot buy something, you have to produce it yourself. So this is just a couple of examples. I don't know if Marco mentioned this yesterday, but this is the cryogenic distillation column developed, whoops, I apologize, what happened? To purify xenon from krypton concentration. So this was developed by the xenon collaboration by the, I think, Mainz colleague maybe, or Karlsruhe colleague, to purify xenon. And there was nothing like that available. It's just, we need to develop it for doing our experiment. And this is another new concept that is electroforming copper underground, because copper is sensitive to activation, so cosmic ray activation. So if you have copper exposure to above ground production, this induce, for example, cobalt isotopes that can have gamma and beta decays that can produce background in your detectors. So here is something about material activation. The process of activation are and P, so the capture of neutrons and protons on your nuclei. And of course, this increases with altitude. So what you do typically in this kind of experiment, you don't fly your components. One example, this is not about dark matter, but I also work in a Majorana neutrino experiment, and we had crystals that are grown in a Chinese vendor, and we ship them by boat. They travel. It's the exposure in 30 days at the sea level is much lower than flying 12 hours. So we transport this crystal without flying them to avoid cosmic ray activation. And again, you have to find a proper way to treat materials. This, of course, depends. Simulation step in at this level, so you have to compute with simulation how much your copper, for example. I say copper because in cryogenic detectors, copper is widely used because it's a very good thermal conductor. So you have to keep your detectors cold, and you have to bring the cold from some machine that make the cold to your detector. So your detector, to keep your detector at 10 millikelvin, you have to connect your calcium tungstate or germanium crystal to the coldest part of a dilution refrigerator. So this you do with some very good conductor. And typically, a good conductor, which is also radio clean, is copper. So if you build your dark matter experiment, you typically store copper underground, and you have to either machine it underground or simulate the amount of time that the copper can stay above ground before the activation starts to be an issue. So if it's not, for example, with copper, if you stay at sea level roughly, at present generation of experiment is not needed to machine it underground, but you have to keep it above ground less than a week or a couple of weeks. So you store it underground for long term, and you just bring it out a piece of the time to get machine and then back store it again, and then you assemble everything underground. So there is a lot of details you have to take care to make the experiments at the level of the state-of-the-art technology nowadays. Okay, so this was just a short introduction, recap of many things you probably heard. Now I will say a few words about the sodium iodine detection. So sodium iodine is nowadays not the primary way to detect dark matter particles, and I will show you why, but it has a major role in the community because of the DAMA claim of observing dark matter. So in the late 90s, well, okay, let's go one step at a time. This is the state of the art. You heard yesterday that the heavy dark matter sensitivity is dominated by dual phase TPC, and at present, the best sensitivity is obtained with the xenon detector, but a new generation of argon-based detectors is also coming to life, so it will be a fight among the two. At present, the best limit is provided by the LZ collaboration, what you see here, but the partner competitors that are the Xenon and TON, so LZ at Homestake in the US, Xenon and TON at Gran Sasso, and Panda X at Jinping Lab. They are, let's say, twin experiment. They are all doing xenon-based dual-phase TPC, and they keep getting better to one another. But at present, the best sensitivity is from LZ, but the twin experiment are almost there in sensitivity. And but let's make a step back, just a little tiny bit of history. So in '84, Drucker and Stodolsky proposed to use superconducting micrograins. Oh, this was a technology using the transition of superconducting spheres. This never worked, but at the time, people thought that micrograins was going to dominate the field. But anyway, they proposed to use micrograins to measure neutrino coherent scattering of nuclei. How is the way nowadays neutrinos generate background in our experiments? Right after that, Goodman and Witten proposed to use cryogenic detectors to detect dark matter candidates. And almost at that time, Drucker, Fries, and Spergel proposed the use of the annual modulation signature as a tool to access the dark matter behavior. So right in that years, there was the, oops, what happened with this? Sorry, again. Oops. The first attempt using the germanium detectors developed for different application to try to extract a dark matter signal. So Frank Avignon and friends at the Homestake mine using a germanium detector did the first analysis to detect dark matter. I think this was published later on, but the preprint was from '86. So it may, to my understanding, it's probably the actual first attempt to measure dark matter in a detector in the lab through scattering of nuclei. But in the same year, Oliviero Cremonesi from INFN tried using a germanium detector in the Mont Blanc lab. I think this was a side activity of the NUSEX proton decay experiment of Fiorini and collaborators. But anyway, Oliviero tried to measure dark matter. No evidence for any of this, but it's the real starting point of the direct detection hunt overall. In these years, from '87 to '95, a number of ideas came out to try to detect dark matter based on, basically all based on cryogenic detectors. CREST, I will speak about CREST idea later on, and you will hear from Bellina ideas from, hints from CDMS and what now is the new phase. So now CREST is CREST 3 and CDMS is super CDMS and Edelweiss is over. But people start to think of using cryogenic detectors to detect dark matter. And there was the first germanium dedicated experiment at the Orville Dam from Caldwell et al. There was the first proposal in '93 of use liquid xenon scintillation. This was not yet a dual phase. TPC was just a liquid xenon scintillator. And in '98, the first result using sodium iodine scintillators, the DAMA experiment at Gran Sasso in Italy, show possible hint of annual modulation evidence. This was a huge boost for the dark matter community. Everyone was trying to reproduce this result and didn't succeed actually, but it was a really huge boost for the community. And not only, it was also really, I think we have to credit the DAMA people for opening our mind with respect to what is generating the annual modulation signal. They started to show us that there is not only the WIMP miracle, at that point, we already start to understand that there was no evidence of supersymmetry at LAP. And later on, we saw that there was no evidence of supersymmetry at the LHC. And at least what people call the minimal supersymmetric standard model was ruled out or had to change panarator pattern and so on. But it was really changed the field. And then later on, the first CDMS result with silicon and germanium detectors, the first result from IGEX at the Canfranc laboratory in Spain, Edelweiss result in Modane in France, the CREST dark matter result with sapphire crystal, and then later on with calcium tungstate, and the first Zeppelin result with liquid xenon, and the first ideas of using dual phase TPC. So this is the golden age of dark matter search. But after this, let's say in the early 2000 cryogenic crystals still had their leading in the field, but from 2010, Xenon 10 experiment and all the other dual phase TPC became that the leading technology, at least for heavy dark matter. But nowadays, this is, let's say, a summary, not maybe super up to date, but roughly you have the Xenon experiments here. You have the Argon experiment trying to reach the same sensitivity. And as you may see, you have what was the cryogenic crystal detectors move to be the leadership in the light dark matter particle. On top of this, we had the Dama Libra signal. So while all of this you see colored in green are exclusion plots, these two reddish islands are a positive signal that you can extract from the Dama results if you assume standard dark matter halo and elastic scattering. So this is, so the very simple. Sodium iodine crystal, thallium dope to be more scintillating. Phototubes phase to that crystal, measuring the rate of events. Super radio pure crystal, to date one of the cleanest crystal ever reached in the field, and not only in the field. As far as I know, one of the cleanest kind of crystal that people was able to build ever. And this is, again, you have a lot of strategy, but after all, this was grown by a French company where a special technician was able, using special tools and just special recipe, to obtain some level of purity that the same company was not able to obtain later on ever. So it was one of the lucky steps, but nowadays there are experiments that are working on this and obtained probably similar result, but after 30 years. So this was the first pioneering sodium iodine experiment with scintillating crystal plus phototubes. And in the beam region of 2 to 6 keV energy region, they saw the first, and I think today the only dark matter compatible modulation signal. This is the most simple detector you can imagine. There is no radiation discrimination, no particle identification, nothing, just pure rate measurement. So you have also to deal with the fact that you have quenching of different radiation and so on. But after all, they look in this beam and they do see an annual modulation signal. This annual modulation signal was then tested a number of times. One thing, just to give you an idea of the kind of things you look at, is the fact that, for example, when people showed that they were not able to see the same signal, we started to cross-check the signal. And one thing that they did, which is quite surprising, is they do see multiple scattering on detectors. That is due to the presence of neutrons. So neutrons have a reasonable probability of multiple scattering over different crystals, while dark matter has no chance to do multiple scattering. And what is impressive of the result is that if you look at multiple scattering interaction, they are not modulating, while this single scattering events is modulating. So this signal, whatever it is, it has a lot of features that reproduce what you expect from a dark matter signal. And then the last phase was called Dama Libra 2. It's 200. So the first phase was 100 kilograms of crystal. The second phase and the third phase was 250 kilograms of the same kind of crystal, improved material. You see everything is shielded with ultra clean copper. Always operator is fully covered with the suits, not to protect the operator, but to protect the crystal from the experimentalists working there. You can notice here, they were using full nitrogen atmosphere. So they had air injected inside to be able to breathe into this nitrogen room. So a really top class, how can I say that? Whatever level of operation to get the most clean detector they could be. And this is what they get at the end. So you have over almost 25 years of data. This is the first, what you see here, the first phase with this bigger modulation, bigger error on the modulation, and then with the improved detectors, the error on with the improved mass and the improved phototubes, the error on the rate points decreased. So over 25 years, they do see an annual modulation with a maximum in June, a minimum in December, which is roughly what you expect from a dark matter signal. I think they had one feature which is a little bit strange, is the modulation they see is larger than 7%. So which is not very easy to understand with the cinematic of the annual modulation. But apart from that, all the cross checks were done.
I think it's important to remember that all the cross checks were done by the collaboration.
Right.
Are not being, I think, as open as some would claim they should be, with a discovery that is worth arguably one of the most important Nobel Prizes in the last.
Absolutely. This is a point. I say positive things to them because, of course, they helped the collaboration to be much more open-minded, but I have to say they were not as open they asked to the others to be. So they, for example, never shared data. No one had access to the DAMA data ever. This, for example, in the community, there is wide policies of open data. Now, many of the experiments you will heard about, I will speak later on of the CREST experiment. CREST experiment has a policy after data are fully analyzed and published, we release the full set of data. So you can go on the archive, find the data release, and look into data. Of course, then it's difficult to look into data that you don't know all the features, all the details. But in principle, if one, I don't know, theorist who is doing comparison of different experiments can collect data of many dark matter experiments, share the data online, and you can collect and extract many information. But yes, this comment is correct. The DAMA collaboration was not really open to share their data and know-how, and this is why people tried in many ways to understand this signal. So people try to extract data from the published spectra and try to analyze with tools. There are ways in you can do, let's say, wrong analysis in which you can come out with a oscillating pattern. But this is really speculation based on the fact that they didn't release the real data and didn't show the details of their analysis.
The company that made the crystal also went out of business, right?
Yeah, well, yeah, something like that. But yeah, at present, there are experiments that are almost at the same level. So anyway, that said, if we take for good that they didn't generate data with the Monte Carlo and things like this, which I think is not the case, under standard assumption, it's very difficult to put on the same plot the DAMA evidence with the xenon exclusion, for example. So the fact that xenon or LZ or PandaX do not see any evidence at 5 or 6 order of magnitude lower in cross-section is very difficult to account. On the other side, nature can be very exotic, and I think we are not here to judge who decided to make nature as it is, but nature is as it is. And And we don't have to go to step back very much to find in the astroparticle physics community things that we are sure that were not like that. Neutrino mixing matrix. I started doing physics, and people was trying to understand neutrino mixing matrix, and now I put the thing in a competition between experimentalists and theorists, but theorists were telling us, look, neutrino mixing matrix has to be roughly the identity, because in the quark sector is the identity, and so natural, whatever natural means, but it's so natural that nature picks the same kind of matrix. And you know that the mixing in the neutrino sector is maximal. It's completely out, far away from the mixing matrix. But theorists were not that happy with this, so told us, well, you see, it's not the identity, it's what we call 3-bimaximal, which I don't know what does it mean, but some numerology to get a matrix in which you get a lot of pi's and e's and exponential inside, and you end up with a very nice symmetric matrix in which theta 13 is 0. So you don't have to look for theta 13 because it's so natural, it's so evident that it has to be 0. And then Diabay came and measured theta 13, and it's 11 degrees, it's not even 0.01, it's just a number. And then theorists come and say, well, you see, not all theorists, I'm just exaggerating, but to let you understand that, I mean, natural is how nature is, not how we think that nature should be. But theorists come and say, well, you see, yeah, it's 11 degrees, but it's 11 degrees because this is an effective appearance on some more perfect theory in which the angle is actually 0. So it's not the theory that is wrong, it's reality that is wrong. It's at this level I was like, I cannot say anything more. But this is just a joke, of course. But I think one very important lesson we should get from things that happen even in recent years is nature as it is. We have just to look at it, measure it, and discover how it is, and then try to understand which are the rules that control nature, not try to impose our rule to nature and hope they respect our rules. So in this sense, at this level, I think there was still room to say, for some exotic reason that we don't understand, nature likes, or dark matter likes sodium iodine and dislikes xenon. This is very strange because xenon and iodine are very near to each other in mass number. So why they should be so different? Maybe the interaction is just with sodium and we don't know. But so what should we do? Well, we should do other sodium iodine experiment. At that point, we are comparing the same result. And this, I think it's what in some way clarify the pattern nowadays. Just to complete what I said on Dama, Dama completed its experimental activity this year. So in 2025, they started the decommissioning of the detectors and the crystallar property of INFN. So if one of us is willing to replicate the same measurement, I think you can apply to Gran Sasso Lab to do another experiment with the Dama crystal and try to measure the annual modulation if you are interested. And I think there will be an open call for this. So think about it, can be interesting. So since there was no way to reproduce the signal in detector different from sodium iodine, people start to build experiment with sodium iodine. There is a number of experiments all around. Anais in Spain in Canfranc Lab, Cosine in Korea, Yang Lab, and now the new Korean Underground Laboratory. There are other. Sabre at Gran Sasso is nowadays, it's delayed with respect to the others, but has detectors that have the same level of purity or comparable with the Dama crystal. So there is a number of things going on. But what is relevant here is that, for example, Anais released last year results. So Canfranc Laboratory in the Pyrenees near Zaragoza in Spain, or 1 hour from Zaragoza, in the tunnel that connects Spain to France through the Pyrenees mountain. And This version of the detector is in data taking since 2017. It's about 100 kilograms of active mass with 2 phototube coupled to each iodine crystal. And finally, they don't see any evidence of annual modulation. Similar results, not that strong. So this was released last year, 6-year data, 4.2 sigma. The oscillation pattern, so the annual modulation is disfavored. I think this year they already reached 6 sigma sensitivity. They haven't released the data yet, but we are expecting them to come. And the experiment is basically over because 5 sigma was the experimental goal. So they're analyzing data. But basically, they don't see any evidence of annual modulation. Cosine has a slightly lower sensitivity, but over 3 sigma, they don't see evidence of annual modulation. So I think at this point, it's difficult to say that annual modulation can be a dark matter. The gamma modulation can be a dark matter signal. What is the gamma modulation? I have no idea. It's really hard for me to explain. In some way, there are things that have annual modulation pattern in nature around the lab. For example, water in the mountain has some kind of, so water that mediates neutrons, for example, has some kind of annualish modulation, but it's not with the same phase, the proper. So, but there are all the attempts so far to explain the gamma signal in different ways didn't succeed. Nevertheless, I think it's difficult nowadays to say that there is still room for gamma signal being a dark matter signal. So I think at this point, the only thing that is still open to do if you are interested is go and use the gamma crystal to do your own annual modulation experiment with sodium iodine. That can be interesting because maybe there is some feature in the Gran Sasso lab, but I don't know. In this, we will see in the sense that the Sabre experiment is now running a prototype in the Gran Sasso lab. So at a similar level of purity, so they may come with some result in the same laboratory. So that should exclude that is a natural effect or confirm that is a natural effect in the lab. There is one other very nice approach that is from the Cosinus experiment. Cosinus is a sodium iodine based experiment which is using instead cryogenic technology, so cooling down crystals at millikelvin temperatures, and this provides double readout. The next step I will to cryogenic detectors and give you all the details that may need to understand. But the nice thing of Cosinus is they can discriminate particle. They do particle discrimination. So this detector that is now almost ready to start at Gran Sasso lab can further scrutinize the Gamma Libra signal as it's the only sodium iodine experiment with particle discrimination capability. But I think at this level, we can learn more on how other particles generated the oscillating signal. But I don't think there is much room. This is personal view in some way, but if you put together all the information I give you, I think there is not much room for gamma signal being a dark matter signal. So this is how Cosinus discriminate different radiation type. This is a prototype they tested. So this can help to understand, for example, since I told you the pure scintillating sodium iodine crystal have no particle discrimination capability, the oscillation can be either in the neutron band, but it can be also in the electron band. It can be some other type of radiation that for some reason that we don't really understand has fluctuation. So it can add some interesting information to understanding gamma, but I don't know. I'm not so convinced that I can see a dark matter oscillation sigma in the Dama region. Then maybe next time I come, I will tell you that they were right and I was wrong. But at present, I don't see much of this. So I should start the second part anyway, or we... They don't seem in favor of this was asked. It's actually so experiment at Gran Sasso are overviewed, or let's say they are overviewed by the lab with the help of a scientific committee. Scientific committee recommended a number of times to make the data open, and also the final recommendation were, okay, well done, but please make the data open to the community. There was no success in this, so I'm not optimistic on this side, unfortunately. Okay, it's really very detector dependent in some way. So you want to measure something. So there is a science case that is appealing for you. You want to detect dark matter in the, let's say, 10 to 100 GeV range. So which detector will you pick? We saw that you need quite a bit of mass. So nowadays, I can tell you that reaching that mass with cryogenic technology is not impossible. I mean, cryogenic crystal detectors, so bolometric detectors, or what people call this. But it's really, really challenging. The largest cryogenic detector to date is for double beta decay search. It's about a ton of mass. Next generation, there will be few detectors in the ton mass range, but going to 10 tons of 100 of tons is really challenging, because so if I have to go for this kind of detector, I will pick, let's say, a dual phase TPC. So we want a dual phase TPC, and then we have to pick which noble gas should we get. And there you have to balance again. Argon seems to have the best background discrimination capability, but is lighter. And in standard assumption, in some way, coupling goes with A square. So should I pick a heavier or a lighter element? At present, giving the state-of-the-art technology development, I will pick xenon, because it's cleaner. It's the technology is way more proven, established. People reach very large masses. There is no, or at present, I don't see relevant showstoppers for increasing in mass and decreasing in background. So we build our own TPC. I go short to make long story short. We make our big water tank, for example, put the TPC in the center. So, and then I want to explore what can I reach with this kind of detector. This actually, I was not. So there is one issue on xenon if you go very large, that is xenon 136 is a double beta decay emitter. So double beta decay emitter means that they have a double beta decay. 2 neutrino double beta decay is the longest lived process ever observed in nature. So it's not a huge background, but if you go to multitons, this means 10 to the 27, 10 to the 28 atoms at all. 10 to the 25 lifetime or 10 to the 24 becomes a relevant contribution to background. So, but on the other side, maybe my feeling is if they go to 100 tons of xenon, they will have to deal with this and probably find get the result. People is enriching xenon in 136 for double beta decay purpose, so they can get probably xenon with reducing 136 for that application. But in principle, if you have xenon 136 and it's not killing your dark matter capability, you can do some neutrinoless double beta decay experiment in the same detector. And then you can do, for sure, neutrino coherent neutrino scattering over nuclei. In this case, with xenon, I expect roughly your energy threshold to be, let's say, order, let's say 5 keV, 5 to 10 keV. Let's say 5 keV, it's reasonable. So you can do neutrino coherent scattering, but you cannot see basically contribution from PP neutrinos. So you can see higher populations of neutrinos. So rates are much, much lower, but you have huge volumes. So you probably can see in supernova explosion, you can see maybe hundreds of counts. It depends on the number of tons, but maybe thousands of counts. So you can be part of the supernova neutrino network that monitor on real time the explosion of the supernova, so that there is a network of warning of a supernova to help everyone to point in the direction and get that signal. So it's, I think the way usually people proceed is you have a science case, you build the best detector for that science case, and then you see which other physics goals are within reach. But in my experience, if you develop an experiment to be multi-purpose, usually you get out with some balance that is not good for any of the purposes. So usually people try to get one physics case, and on the other side, it is true that detectors develop for something completely different. Physics of atmospheric neutrino was basically started by people trying to do proton decay. And then nowadays, proton decay is still far away to reach, and neutrino physics is fully established, and we understand a lot of things in the mixing. So it's a very good attitude to be ready to look whichever physics signal is in your detector, but it's I will not build a multi-purpose detector engine as a starting base. I will try to focus all the features, since a detector is always a balance, because the ideal detector doesn't exist. This is a message for those of you doing projections for the experiment. The 100-ton zero threshold or infinite mass experiment doesn't exist. So we have to deal with the fact that experimentalists have to build real detectors. So million tons experiment are far away to be reached. Maybe in, our high energy neutrino colleagues instrumented a cubic kilometer of the Mediterranean Sea, and they do see. So you can build big detectors, but it's again a balance, because in that case the threshold is very high, and you see sperm whales fishing around. So each experiment has its own balance and things too. But yeah, that's